So in this video, we're going to resume our lectures on interpolation, and we're going to talk specifically about Lagrange interpolation, which is a simple method, a simple trick to actually compute the coefficients of a polynomial that interpolates given some data points, right? So let's recap a little bit. We started talking about interpolation a little while back, and the whole goal of interpolation is you're given some data, and the data here were written in the form of a vector, a given vector. So f is a vector here, whose entries are f of 1, f of 2, and so on, all the way through f of n. So we can say that this vector f belongs to the set of ordered numbers in Rn, right? And then we're given an interpolation model, and in the past we've written this model as v of x as a sum over some coefficients times some other functions, which we can call this basis functions for now. And in the past, these functions, phi here, were polynomials. So for example, in the past, we wrote phi of p of x to be equal to x of p minus 1, for example. We also investigated other examples of these basis functions. But nonetheless, this was our setup, and then we saw that if we did some work, we could write this linear system of equations, this problem of finding the polynomial that passes through the data points as a linear system of equations, where again, this c is here is a vector of unknown coefficients. So we seek the coefficient c that we multiply and add these basis functions with, that gives us exactly our vector x. And this was solved via a matrix times an unknown vector equals another vector. So in the past we used to call this ax equals b, so now we're calling ac equals f. The meaning is the same, and you can apply Gaussian elimination, for example, here to solve for the coefficients. But to do that with anything more than a 2x2 or 3x3 by hand would be cumbersome. Of course, we have computers to do this with nowadays with MATLAB or Python. So today, in this video, we're going to learn how to actually solve for these coefficients by hand, so to speak. And the whole trick here is to notice that that certain simple things can be done. For example, let's say we're given a vector, some data points, and now the data points really are just 2 points. Right here is our point number 1, evaluated. So we have f at evaluated some point x0, and we have f evaluated at some point x1. Right? And we would like to find, for example, some function. In this case, this will end up being a line that connects these points, so that if I want to find the value of my guessed function in between the coordinates x0 and x1, I can do that with no problem. So to do this, let's make an observation. Let's first find the line that passes through the data x0, or f at x0, but the line will also be 0 at x1. Right? So let's first find this line, and then conversely, let's find the same line, a similar line that passes through f at x1, but it's 0 at x0. So let's call this line here line 1, or let's say line 0. So this is going to be, I'll call this L0 of x, and the orange line I'll call L1 of x. So let's look what L0 should be, or what it can be. So in this case, we can see that, let me state this line. Let me state, and then we can analyze it. So this line will be x minus x1 divided by x0 minus x1 times y0. Let's look at this line and see if we can plot it. Let's begin by inserting here x0 in the place for x. So what is L0 at x0? Well, if I plug in x0 here, I have x0 minus x1 on the numerator and x0 minus x1 in the denominator. So this fraction here will be 1. And 1 times y naught, or in this case, y naught, I should mention, is our f at x0. Right? So if I plug in x0 for my x here, I essentially end up with a line that says this is equal to y naught, which is equal to our f of x0. So we verified that this line does indeed pass through this point. Does it also pass through this point? So let's do this calculation. What is L0 at x1? So if we plug this in here, for x1, we have x1 minus x1, which is 0. So 0 times anything is 0. So we have that in this case, this will be 0. So we have verified that this line L0 is indeed this line that we plot here, right? It passes through y0 or f of x0, and it passes through 0 at x1. Now, let's do a similar computation and evaluate, come up with a line for L1, right? Which again, once again, it's going to be this line. So I'm going to again state this line, and then I'm going to explain it. So this line is going to be, let me use the same color as above, x minus x0 divided by x1 minus x0. And this is going to be times y1, which, like before, we're going to equate to y1 is our f of x1. It's just simpler. It's shorter to write y1 instead, which, again, are given data points. So here's our line. So let's look again, do the same exercise as above, and see whether L1 at x1, what is that? Right? So we have to plug in x1 into this variable. So x1 minus x0 over x1 minus x0 is 1. So that works out. Times y1, this is y1. Which, again, we stated this is going to be f of x1, right? We're abbreviating f of x1 as y1. Let's do the same computation and evaluate line 1 at x0 and see what that gives us. Well, just the same as in the example above, we plug in x0 here. x0 minus x0 is 0. 0 divided by anything or other than 0. 0 divided by a number or 0 multiplied by a number is still 0. So this line does what we intended it to do. It is indeed this line, right? Because we have passed through this point here, and we've passed through this point here. So now let's look at what happens when we sum this line and this line. In particular, we're just going to consider what happens to the sum between x0 and x1. Well, we can quickly see this, that at x0, so we're computing again. Let's compute this model, which we called v of x before. So let's call the same thing. And we're going to plot what is v of x, and we're going to make v of x L0 of x plus L1 of x. So let's plot this function. Well, we already stated that L1, so let's start at x0, right? So what is V at x0? That's going to be L0 at x0 plus L1 at x0. This guy here will be equal to y0 plus 0, right? We already stated that L1 at x0 is 0, so I just plugged it in here. And L0 at x0 is y0, or f of x0, which is a given point. So we're starting here. Right? We're starting at this point here. Conversely, we can do the same computation to find out what is V at x1, and that's going to be 0 plus y1. So we are going to, this line is going to end over here. And in between, right, we can see this graphically. Here we're going to add this much to this much, right? And here we're going to add pretty much twice this value, so that will be here. And we keep going, right? This much to this much is here, this much to this much is here, and so on. So we can safely say that this is an equation of a line that joins these 2 points. And again, we just limited to what happens between x0 and x1. So finally, right, so the equation that we end up with is going to be V of x will be line 0 plus line 1. And what's the equation for line 0 again? So that's written up above. So this is going to be x minus x1 divided by x0 minus x1 times y0, which again is given as a data point, plus the line for x1, line 1, and that's going to be x minus x0 times y1 divided by x1 minus x0. Right? So we can very quickly find a polynomial that passes through 2 data points. So let's expand this idea and figure out a formula that does the same thing now for a quadratic function, or a second order Lagrange interpolation method. Right? So let's redo this thing down here below. So let's add another axis to our plot. And basically the same example as before, right? We're going to have now we're going to have 3 points. So let's write these points again. We're going to have, let's say, x0, let's say x1, and let's say x2. And once again, we're going to have our function here, right? So let's say this, and I don't know, some other value here, right? So this is going to be, over here we have f of x0, f of x1, f of x2. And now with 3 points, it's impossible for us to find a line that passes through any given set of 3 points, right? That may not always be possible, but we can certainly find a quadratic function that passes through all of these given points. And this is what we're going to do. And we're going to, once again, require that this quadratic function be a sum of 3 quadratic functions. Right? Quadratic function number 1 will pass through the first point but be 0 in the other 2 points. Quadratic function number 2 will pass by the second point but be 0 at x0 and x2. And likewise, quadratic number 3 will be passing through fx2, but be 0 for these two other ones. If we find these, we can add these three quadratic functions together safely, and we know that the result will pass through all the points. So what is the overall formula? Let's write this again, and then I'll explain. So this our model now, v of x, will be a sum of three lines, right? So it's going to be not lines. These are not lines anymore. These are quadratic functions. So, but it will be L0 of x plus L1 of x plus L2 of x. So let's just interpret these L's now as quadratic functions rather than lines. But let's figure out what they are. So let's look at this first one, and let's look at this function here. I'll write it and then explain again. X minus x2 divided by x0 minus x1, x0 minus x2, and times y0. So this is going to be our first quadratic function. Let's ask ourselves, what is this? Right? So let's say here we plug in x0 for x, right? So x0 minus x1 cancels this bottom one out, and x0 minus x2 cancels this bottom one out. So this fraction here will be 1. 1 times y naught is y naught, which is, once again, right? So we call this y naught, and we call this y1, and we call this y2, right? So that's correct. Let's plug in the values for x1 and x2, and hopefully we'll get 0, right? So let's plug it in. If we plug in x1 here, x minus x1 is 0. So everything else, so long as this there's no zeros here in the denominator, we are in business. The whole thing will be 0. Let's plug in 0. Let's plug in x2 here, right? x2 minus x2 is 0. So the same thing. So this term checks out. This term is going to be passing through this point, but it's going to be 0 and 0. And note that this is a quadratic, right? It has x multiplied by x here. So now we have sort of the formula, the template for the other terms as well. So this is going to be x minus x0, right? So these essentially have to be the roots of the quadratic in the other 2 points. So x minus x2. And here we're going to divide by x1 minus x0 and x1 minus x2, and this is going to have to be equal to y1 plus x minus x0. So let's do the third quadratic function the same way. X minus x1 divided by x2 minus x0 times x2 minus x1, and this is going to be equal to times y2, right? So our end result, now we solved for a quadratic function that passes through these 3 points, and our result is written here. We don't have to solve for those coefficients using Gaussian elimination or anything. These coefficients are given. If you expand this out and regroup them, you can get the coefficients right away, right? And we can expand the same technique. So for example, if we're given 4 points, we can now find a cubic function that passes through all these 4 points, right? If we're given 5 points, we can find a polynomial of power 4 that passes through all these 5 points, and so on, through the same technique.